there's a lot of patterns in certain types of graphs. The ones that I have here in particular are no exception. And what I want us to see is what happens when we put in different numbers for n in an equation like this. R is cosine of n theta. So what's a cosine of 2 theta look like? Cosine of 3 theta, 4 theta, 5 theta, etc. How do these graphs look? Well, in order to do that, we're going to need to make some changes to our calculator. So first thing I want you to do is go to the mode key. It's right next to the second key. And first thing, let's start out in degrees. It's just going to be a little bit easier to think about in degrees. So change over to degrees. And then the line below that, choose polar. So make both of those changes. When you got those changes done, let's hit the y equals key. And you should notice a change in the y equals key. So hit the y equals key. What's changed? Yeah, you've got an R there as opposed to a Y. Okay, that's good. There's some more changes. But let's type in cosine of 2 theta. So cosine, then the 2. What's that? I haven't got there yet. All right, cosine of 2. And then when you type the x, out comes a theta, because you're in polar mode now. If you take a look at that, if you take a look at this, there's several different modes here. X is your regular rectangular. You got T, which is for parametric, theta, and then N for sequential. But we're in polar mode, so cosine of 2 theta. Now let's set up our window to match the one that's down here. So in the x direction, we want to go from negative 1.5 to 1.5. In the y direction, negative 1 to 1. But there's some more stuff before we get there. I talked about how these graphs are created, how you graph something in polar coordinates. The way you do that is by plugging in values of theta and then getting values of r. So what the calculator is going to do for itself is kind of something like this. It's going to set up a bunch of different values of theta, and for each value of theta, it's going to compute a value for r. What you're doing here is telling it where to start. We're going to start with theta equals 0 all the way up to 360 degrees. And the theta step says, okay, first you're going to plot it when theta equals 0. Then you're going to move up to theta equals 5, and then theta equals 10 degrees, and then 15 degrees, etc. X min, we want it as negative 1.5 to 1.5 for X max. I'll leave this at 1. Y min from negative 1 to 1. And these give you what's called a square window. But you should be able to hit the graph key at this point and get, cool. 4-leaf clover. All right. Nice. Let's see what you got going. Okay, if you're getting an error that says invalid dimension, what you should look for in the y equals menu is to see if one of your plots is turned on accidentally. If one of these is highlighted, just go up there, press enter to deselect it. Now when you hit the graph key, cool. All right. Still got an error? No, it works? Yeah, give yourself one of these. All right, good deal. All right, is everyone able to get that? All right, so what I'm going to do is put you in groups. I want you to graph the remaining 3 of these. So there's several here. We got the cosine of 2 theta. We can draw that one in. I'll let you do that. Draw these 4 in.
Or just a shape?
I mean, just draw the shape. I mean, you don't have to be terribly exact. You should see a pattern emerge out of this. This, by the way, down here is r equals cosine of 6 theta. And this graph down here is r equals cosine of 7 theta. So see if you can't figure out that pattern. Let me put you in groups. Pause. It's up, work on it together.
We just pick our own groups.
I'll pick some groups for you. So, across the back row. 3. Press 1, 2, and then.
This takes like 3 seconds.
Cool. And then you two can be a group 2.
Okay. Thank you. Do you want to just compare and stand up? Mine are ugly.
It's alright. It's
Yours
just
were
you
probably
should
better than
see a
mine.
pattern regardless of how good or bad your drawings are. Alright, so work on it a little bit, see if you can't finish up the different graphs.
Glad I'm not an art major. Should we go when we're done?
What?
So if we could just go when we're done. Yeah.
If that is on,
We changed it in class to the X width and yeah, some of these, like you can tell, like this one right here. Oh yeah, like the one that
What?
got any witnesses?
Autograph them all at once.
So good art. It was yours. You're gonna graph all of them?
Oh my god.
I wonder if you change it to sine.
I wonder if we change it to prettier colors.
Oh, sine does change it.
You should see a pattern pretty quickly.
I see a pattern.
See a pattern.
Looks like they look like flowers.
That's the pattern.
I think the pattern is when n is even, it has
Okay.
2 n petals, and when it's odd, it just has 1. It's 2.
But there should be a pattern there. You should be able to predict,
When it's odd, it's just n.
what's
So there's
going
always
on in
one.
terms of the number of leaves.
For
Your
3
goal is
and
to be
5,
able to
it's just
predict the
3 and
number
5,
of
but it's
leaves
2 and
you
4,
get
it had 4
in these things.
Oh, so 2 it's double. If it's even, it's double. And if it's odd, it's just the number that you get.
That's what I think.
So 4 is 1, 2, 3, 4, 5, 6, 7. Oh, there's 8, so it's times 2. Math.
What do you know?
So much
Math. So cool.
Wow. Look at that one. That looks like a 10.
Oh my gosh, that's so cool.
Did you do 10?
I did do 10. Look, it's pretty. It looks
kinda
like
cool.
I could do
it
100.
looks
When I
like,
was-
what's it called? Like one of those, the fuzzy ball things that you blow. Dandelion things. It looks like a dandelion, like the fuzzy ones.
Okay, yeah.
What's the Oh, it looks like the sun.
Oh my. What you put, 12 or 20 or something?
Let's put 1,000.
Crazy. If you do that, reduce theta step to like 1 or a half, because otherwise you're not gonna have a fine enough graph in order to see that.
Well, I did like a lot of zeros, and it doesn't look. It looks really weird.
Yeah, that's what you said. You have to reduce it. Cosine. Let's do tangent. I feel like I should be on an acid trip right now.
Okay.
Just do some LSD while making.
I'm inspiring you.
I've never done it before, so you might as well.
YOLO.
I feel like this is what the hippies do. Because they have all those
Somebody got that one. Yeah, I heard that one too.
I don't understand what you mean. Yeah, I just saw it. It looks like one of those
This is your mind on drugs. Yeah, so theta's really spiky. Because that's 5. Well, that doesn't make any sense. That's 5. 5 theta. Tan 5 theta. That makes no sense.
Missing like
I'm gonna graph all of them with 2 theta.
2 theta? Tan.
proximal phalange.
It's so literally looks like
We're just. Oh, you should do
Spoken like a
tan,
doctor.
cosine.
do all
Doc,
of
it's
them.
gone.
2 theta.
Proximal phalange, proximal, middle, and distal.
Theta.
Yeah, he wants to be a doctor.
I would trust somebody to let me do surgery.
Cosine.
Yeah.
I wasn't that great of a carpenter, so I didn't want to be a surgeon. It's pretty much the same thing if you go to orthopedics.
Yeah, but how often as a carpenter did you have leftover parts?
Taking a lot of not so much math though.
Oh my god.
You said you were gonna go see Radians, did you?
See where?
Like it's gonna start exploding.
Oh, I did. Yeah. I actually ended up seeing his partner, Keller.
Look at that one.
Wow. That's pretty.
This one's my favorite.
How many did you put?
I put like. I did all of them. You should get a tattoo.
I might.
You made it yourself.
Okay, so what kind of pattern did you see emerging when you looked at all these things?
Doubles for 2s. Evens.
So this was cosine of 2 theta. If I do cosine of 3 theta, then I only get 3 flowers. If I go back to cosine of 4 theta, then I get 8. So what's the pattern here? Yeah. Odds tell you how many there are. Evens are going to be double. Now, if you want to understand why some of them are double and some of them are not, then follow along with this. Go to your calculator, the y equals key, and skip across the equal sign to the mode of your graph. Now, this is going to look different if you got a TI-84, the non-color version, as opposed to the color version. Somebody with an 84 or regular 84, bring theirs up here. Now, with the color version, if you press the enter key to the left of the R1, you can go down and up. You can change the style of graph. This is the style that you want right here. The little dot, kind of like the male symbol, Then the press OK. Now, when I graph this, and let me do it for those of you who have a calculator like this. So, if you go to the left here, press enter. That gives you a solid line. I don't want that. Press enter again. That's the one I want. Now, what this does is it puts a cursor on the graph. So,
It's like a little bee.
somebody here had a 2 theta here. Let's do, or a half theta. Let me do a 5 theta. But watch what happens when I do 5 theta. So I'm going to get the graph. It graphs up my 5 leaves, but then it retraces those 5 leaves. Whereas if you had, say, an even value for theta, like we do here,
Third diagonal.
it doesn't retrace things. So when it's odd, you get some retracement. When it's even, you don't get that retracement. So let's do an odd one here. Let's do 5. You can see it retraces itself, and it doesn't do that when n is even.
Oh my god, that looks
So,
so pretty.
so that's why you're getting that kind of strange. It doubles. Really, I mean, you could say, well, there's 10 leaves here, but 5 of them are the same as the first 5.
Kind of like what an Etch-a-Sketch is.
Yeah, Etch-a-Sketch. I'm surprised anyone still knows that. I thought I was the only one old enough to know Etch-a-Sketch. But yeah, it's like Etch-a-Sketch and Spirograph. If you remember those.
The stencils.
Yeah, the stencils with you
I was
run them
really
around.
bad at that. I didn't have the patience.
I think I lost all the parts. Is what happened to mine. Okay. Yeah, the odds it traces over itself. So realistically, what's that?
Or like the ones with
Yeah,
the lights.
yeah, you'll see it when you have your graph in that mode. Okay, if you had it, you're just not going to see that retracing part. Now here's something else to give you some more insight onto what's going on. Let's go to the window. Let me just go, instead of going 0 to 360, let's go 0 to 180. Now, when n is odd, I still get my full graph, right? Still works. But if n was even, say a 4, well, then I'm not using enough values for theta to get the whole graph. I'm getting half of it. So a little more insight as to what's going on with these graphs.
So if you expand your window to like 720.
Good question. If you expand it to 720, so let's do that. Let's go up here and do 720. Then it's just going to keep on repeating, going over and over and over again and again and again. Now there are some graphs, and I'm not really going to try and work with you on them here, but there are some graphs where you have to change your window up to 720 or 1080 to get the entire graph. But we're gonna be, this is a kinder, gentler math class. We're gonna stick with graphs you can get between 0 and 360. Should we do this in Radians as well? Let's practice it in Radians real quick. So what would our Windows settings look like in Radians? Well, first of all, let's go to the mode key and change over to Radians. So change to Radians. Now, instead of 0 to 720 or 0 to 360, I want 0 to 2 pi. Now, after you enter the 2 pi, you're going to lose the pi symbol. It's going to be replaced with 6.28, etc. Theta step, I don't want that to be 5 anymore. I want that to be something pretty small. Let's try 0.1 to begin with. Because if I chose, well, I'll tell you what, let's take a look. What if I left it at, say, 1? Yeah. It's just kind of way off, right? Because it's plotting, at theta equal 1, at theta equal 2, theta equals 3. It's doing this in radians. So each one is like, 57 degrees. You're only getting a handful of points, right? So you need more points. So let's make this, let's go to 0.01. Now this might be a little bit too much. It might tax our patience. Because now you're going to be pointing, you start out at 0, then 0.01, then 0.02. It's going to take a while. And you can see that it's much slower than it used to be, although you're getting a smoother graph than what we used to.
It's about how fast my brain works. I'm getting a more choppy graph.
Did you convert to degrees? Is your mode in degrees?
I think one in radians.
Oh, yeah. Are we in radians? Are you in radians? Let me see your graph. It should be smooth.
It is smooth, but it's like
Did you,
jagged.
what's already?
Your window's a little bit different than mine. Window.
Oh, the petals are smoother. Oh, that's so pretty.
Your Y-min should go from -1 to 1. So, yep.
Now we're just gonna be sitting in class making pretty pictures.
Okay, no, I still think it's just because it is. I'm just curious. Like, to me, that's more jagged.
The pixels on that aren't. You don't have as many pixels
Right.
there as I do on mine, so
Is that what?
that's part of why. I think I get like 264 across the screen. You've got like 94. Okay. So we can make predictions about these graphs just based on the style of that equation. Yes, sir.
Were we just doing cosine 4 theta?
Yeah, this one looks like cosine 4 theta. Yes.
And then we're in
So really to figure out.
Radian, and our window is set between 0 and 2 pi for theta.
That's, yeah, I'm not getting anywhere near what diagrams.
Yeah, but that's really, really slow. I wouldn't make it that small. Do 0.1 or at most 0.05. So here's 0.1. That looks pretty good. Okay.
So really all that you have to do to figure out this number, if you're not given it, is count the number of petals and divide by 2. And that will give you this number here.
Yeah. For even numbers.
For even.
Right.
For odd, you have to count them all.
Right.
That's
Okay, so let's take a look at the sine graph. Now, what we've been working with was the cosine. Are things going to be much different for the graphs of the sine?
yes.
Not really. The only difference is exactly where these leaves are located. Now let's compare this one here to the graph of sine of, or cosine of 2 theta. The only difference there is that the graph of cosine of 2 theta
They just
started out on the x-axis, right? So your first leaf had an axis of symmetry right on the x-axis. Whereas with the sine, it was tilted a little bit. That's what it looked like for the sine, if this was your x and y axes.
now the smaller the theta step, the slower the function will be.
Well, it's just plotting more and more points. Yeah. So what happens is if theta step is 0.1, then I start at a 0, 0.1, 0.2, 0.3, all the way up to 6.28. And after I get there, then it stops. So if I did 0.05, well, that's going to be twice as slow because I'm going to be plotting twice as many points. So that's why it can really slow things down if you choose a very small theta step. You don't want to choose theta step to be too big either. So just play with it, find something comfortable. It's going to depend if you're working degrees or radians.
Why does tangent look like a spider web?
I think there's more to the graph of the tangent there. I don't have it in mind like I do the graph of sine and cosine. There's more that goes on to that. Let's hold off on that. All right, so on the back of your sheet, you can kind of fill things in. So these are the conclusions that you should have for the cosine in terms of the number of petals, and it shows us a nice relationship between this value in front of theta and the number of petals. If it's even, then you get twice as many petals as this number. If it's odd, it's the same number. So that holds through all the way down. Same thing is going to be true with the sine graph. 2 and 4. 3 and 3. 4 and what? 4 and 8, etc. The only difference, like I said, is where that first leaf is drawn. You can kind of see it and predict it with the cosine. What's the cosine of 0? Your graphs are always going to start out by plotting things at theta equals 0, and then r is whatever. What's the cosine of 0? Cosine of 0 is 1. That's why your graphs of your cosine functions start out here. What if I dealt with instead of the cosine, what if I had the sine? What's the sine of 0? Sine of 0 is going to be 0. So your sine graphs are going to start out right here at the origin. and then they're going to loop out. This maximum point is going to be when you evaluate the sine of 90 degrees or the sine of pi over 2. Then it's going to loop back in, and then out and in and out, etc. This axis of symmetry, in this case, is at pi over 4. And so on. Trying to think, where's this one going to be? Interval for theta. That's to trace out one graph. Nah, I'm not really going to make you know it. You can experiment and figure it out. To trace out the whole graph once, you could use the interval 0 to 2 pi. Here, to trace out the whole graph once, you just need 0 to pi. And that pattern is going to repeat itself all the way down. If you have an odd number for a coefficient, it's going to be 0 to pi. If it's an even number, it's going to be 0 to 2 pi.
So sine's gonna or cosine's gonna always be the 0 because it always starts at origin, right?
Yes, sine's always going to start at the origin. Cosine's going to start on the x-axis. Let's look at some other graphs and see if we can't make some predictions. We saw, for instance, the graph of problem number 38 a little bit ago. Wrong one. Where's Desmos? There we go. Yeah, here's graphs like 38. Let me just change it up a little bit. 38 was actually the sine of theta plus 1, or 1 plus the sine of theta. So this is the shape of a cardioid. Does everyone have, where is it? Yeah, here we go. This sheet. So let's take out this sheet and start getting familiar with some other types of graphs. In particular, a couple that I want to highlight would be your cardioids, here and here. We can also look at circles. And we dealt with our roses. So these are all, these last several here are all basically different forms of what we just dealt with. There's a lemmason and a lemmascate. I'm not going to work with these for you guys, although they are kind of cool shapes. The difference about these is that on the left-hand side, you've got an r squared. Now, we're going to leave those alone. No, but it's pretty cool. Yeah, it is pretty cool. In fact, the spiral of Archimedes is a way to move water that's been around for a few thousand years. Yeah. You'll see that shape, spiral of Archimedes, and things that are related to that. You'll see it in hurricanes, shape of a hurricane, spiral galaxies, the path that a hawk would soar in as it circles its prey and looks down. Yeah, because you're maintaining a constant angle of like 40 degrees, and you're looking down. So lots of applications for that. If you've heard of the Fibonacci sequence, Fibonacci numbers, it's related to that stuff as well. So a lot of good stuff. Let's look at a few here from problems 37 to 40 and see if we can't make some identifications as to what kind of shapes that we're dealing with. So the first one I want to start with is problem number 42. Does this give you enough? Yeah, I think we're missing something. Let's, bless you. Two minus 2 cosine of theta. So r equals 2 minus cosine of theta. So, problem 42. Maybe it'll help us out to put something here that's kind of understood but not really written, and that is a 1. So this is 2 minus 1 times cosine of theta. And that just gives us, another value here that's part of our equation. Let's see if we can't figure out what type of shape this is. So, in order for this to be a cardioid, these two things would have to be equal. In other words, these would both have to be the same, and they're not. So it's not a cardioid. Is it a lemmason with an inner loop or a lemmason with an outer loop? Well, not with an outer loop, but let's take a look at it. The next one. If it's a lemmason without an inner loop, then B has to be smaller than A. Well, what's A and B in this particular case? This is my A, and this is my B. Does it fit one of these? Well, it'd have to be the top one, right? Because it's got a cosine. 2 minus 1. So that makes B 1. A is 2. Looks like it fits this. Looks like a lemmason without an inner loop. It is different than the handout. This is in the book. The handout didn't have this one on it. I'm sorry, I have to get you another one. But on an exam, I'll get you exactly what you need and nothing more. So this is a lemmason without an inner loop. Let's actually compare this to the graph. Let's see that works. So r equals 2 minus cosine of theta. Now let's just steal a theta from up here.
So mine just looks like a circle.
It's not quite a circle. If you notice on this one side, it's a little bit flat.
Like a flat circle.
Yeah, it's a flat circle. It's a circle that has been kicked on the right-hand side. Let's try a different one.
Can we just do this first and then just think?
It's called a lemmason without an inner loop.
So we
Yeah. Well, with an inner loop, tell you what, let's just take the same equation and switch up a couple letters here real quick. So what if I had r equals 1 minus 2 cosine of theta? Then here's my A, here's my B. How does that compare to what I have up here? Well, A is smaller than B, right? So that would be this stuff over here. So what's the graph of this one going to be? It's going to be a lemmason with an inner loop. So lemmason with an inner loop. Lemmason without an inner loop. And that's what I'm going to look for you, is to be able to decide what's what. Let's see that we actually get a lemmason with an inner loop. When this number is bigger than this one, you're going to get that inner loop. Let's just switch these up. A 1 here and a 2 here. Ooh, and there's your inner loop. Cool.
So we need to know the lemmason.
Sort of. You'll be given this. Let me see. Let me switch over here. You'll be given this and asked to do exactly what I'm doing right now, which is identify what you're looking at in terms of a cardioid, etc.
Okay. Will we have the second half of that as well?
Um,
I can't even read it. But...
yeah, the second half is going to be your roses.
Right. Are we going to have those
Uh,
I mean, you might as well just copy the whole graph if you're gonna do it.
Probably. We don't need Lima skates. I'm not going to deal with Lima skates. Let's do a couple more. What if I gave you... In fact, why don't you try and identify these next two? R equals 2 plus 2 sine of theta. And R equals 3 minus 4 sine of theta. Try and figure out what shapes these represent. You can double check yourself by graphing these things. That's fine. Nothing wrong with double checking yourself. You might want to work with these things first and then double check yourself. There we go. Okay. So how about the first one? Cardioid. Perfect. How about the second one?
Limicon with inner loop.
Yeah. Limason with an inner loop. Yeah, there's a guy in the NFL who has a name with one of those little things in it. I forget. It's a French character. Je ne sais pas. Non, je parle français très bien. I don't know. But there's a guy in the NFL that has that as part of his name. He's the first one. What's that? It could be. I think it is. Anyways, all right. So we got those two. Roy McKenzie, you asked me about where do we use this stuff. One thing that comes to mind here, and that is the description of the orbits of the planets. All of them have a description that can be written in this form. So, planetary orbits. Now, planetary orbits are in elliptical shapes. And all our planetary orbits can be written like this. A times 1 minus e squared over 1 plus e cosine of theta. E is something called the eccentricity of your ellipse. So the bigger E is, the less like a circle and the more like an oval that your orbit is going to look like. In particular, for Earth, that would be 92.73 times 1 minus 0.0167 squared over 1 plus 0.167 or 0.167 cosine of theta. So that's in polar coordinates, but these are the kinds of equations that you would have to use if you're launching satellites or traveling to the moon or even between Earth and Mars. Yes?
Yeah, how do you remember all that?
Oh, I don't have that memorized. I have that written down.
Oh.
No, I don't mean to pretend to have that. Yeah.
Never miss an anniversary.
No, yeah, the best way to remember your anniversaries is to forget it once. Yes, sir.
For like the lemniscates, is this applicable to like orbitals for electrons and stuff like that too?
It could be. It could be.
Randomized.
I My physics was limited to the macro level, the stuff I've done at the micro level. We never got into the actual calculations there. Okay. Homework.
We made shapes today.
We made fun shapes today, yes. Try 37 through 53, and the goal is to identify the polar equation like we did with these last several. You don't necessarily have to graph it, although graphing it's really, really cool. Yeah, you just have to tell me, is it a limacon with an inner loop, without an inner loop, is it a cardioid, etc. It's actually more information you can get out of that, but that's good enough for now.
So we'll be given that. We don't have to remember it.
You'll be given a copy of this page on 324. So right here, pause the video, take a screenshot, and print it out. That's what you'll be given on next week's exam.
What was the homework? 35 or something.
See ya.